Sometimes polynomials can't be approximated about 0. So when that happens, then we have to modify the definition of an approximation a little bit. So when we talk about approximating these non-polynomial functions with a polynomial expression, if we notice here, if it can be evaluated or centered at 0, then we get this real simple pattern like we've been working with the, we call that a Maclaurin polynomial when it's centered at 0, where we just have the function centered at 0, and then we have this x term whose power matches the degree of the polynomial. When it's not centered at 0, when we have to center it at some value, we'll call it c. Then we have to go and evaluate the derivative at that point. That point of interest is where we want to match the value of the function and the value of all its derivatives. So we have to evaluate it at that we call it a center, which is why we use the variable c. We evaluate the function at all its derivatives at that center, and then we also have this term here then that's kind of an offset term basically, because we're offsetting this polynomial function c units to the right or to the left, so that we can offset the center from 0 to that location c. When we do that, we call that a Taylor polynomial. So the Taylor polynomials, that's kind of the new term for this section. These Taylor polynomials are when they're centered at some value c, where our Maclaurin polynomials, which is what we've been talking about up until now, our Maclaurin polynomials is a c equal to 0. So we're centered at 0 here. So if we take a look at this, it says find the Taylor polynomial. Find the Taylor polynomial centered at 8. Okay, for this. And so if we notice this is a cubic, so we're talking about the cubed root of x, and so if we look at that cubic function, x to the 1/3 power. Where's my cube root? I think it's under math. Yes, it is. Here we go. The cubed root of x looks, something like this. And we could center this at 0 because we can evaluate the function at 0. Well, I take that back. We cannot center this at 0 for reasons why I'll get into in just a second. But we don't have to center this at 8. We could center it at maybe another perfect cube like 1, or 27 is another perfect cube that makes finding the values of the derivatives pretty easy. So when we take a look at this, the process doesn't change. We still have to evaluate the function at 8, and we have to evaluate all of its derivatives at 8. So we're going to have to calculate the first 3 derivatives here. And so the function is x to the 1/3 power. It's going to be easier to differentiate if you think about this power as a fraction rather than a root. So the first derivative is going to be 1/3 x, and then we have to subtract 1, so that's the minus 2/3. And then the next derivative is going to be minus 2 over 9, x to the minus 5/3. And then the next derivative after that is going to be positive, because we're going to have negative times negative, 10 over 27, when I multiply those two things, x to the minus 8/3. And so if we look at this, x to the 1/3, if we look at this, this is really 1 over 3x to the 2/3. And this is really negative 2 over 9x to the 5/3. And this one is really 10 over 27x to the 9/5. And so when we see these expressions written, that's why we cannot approximate at 0. Because these are not defined at a value of 0, since the x is in the denominator. So, there are times when we just cannot do a Maclaurin approximation. We have to do a Taylor approximation. So this one is going to be centered, if we, let's change the window in here a little bit. Let's go from minus 5 to 5. And we'll do that all the way around, minus 5 to 5. So we're going to evaluate, oh, I can't do that. I got to do something bigger than 5. My mistake. So I guess I will have to stay at 10. Let's just do zoom standard. There we go. I have to stay at 10 because I need a C of 8. So if we look at 8 here, 1, 2, 3, 4, 5, 6, 7, 8, we're right here. So we're going to center it about this point here. Actually, so what I'm going to do is I'm going to take my x's and I'm going to take them from 0 to 16. Just so that we're kind of in the middle of this window here. So we're going to center that about the middle of the window. So 0 is not going to work because we can't evaluate 0. We're going to evaluate these at 8. That's our center. So 8 to the 1/3 power is 2. The derivative evaluated at 8, that's going to be 1 over 3 times this. And 8 to the 2/3 power is 2 squared, which is 4. So that's 1 over 12. And evaluating the next derivative at 8 is going to be, let's see, this is 8 to the 5/3 power, that's 2 to the 5th, basically. So 2 to the 5th is 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So that's negative 2 over 9 times 32, which is 288. So that's negative 1 over 144. And then evaluating the third derivative at 8 is 10 over 27 times 256. That's what 2 to the 9th is, which is reducing to 5 over 3,456. So there are all the derivatives. So now that we have the derivatives for the first, up to the third derivative for our third degree polynomial, we can go ahead and write this polynomial approximation. And so this polynomial approximation looks like it's a P3 because we're going up to a third degree polynomial. And so with the Taylor, we have to add this offset here with a center of 8. So we have the value of the function at the center, which is 2, plus the derivative, 1/12, times, and this is the new part, we have to subtract off the center here. So the center is 8. So we have the derivative, x minus the center to the first power over 1 factorial. And then the second, to get the second degree term, we take the second derivative, negative 1 over 144, x minus 8th to the second power over 2 factorial. And then to get the third degree term, we take the third derivative, 5 over 3,456, x minus 8 to the third power over 3 factorial. So that's the expression of the polynomial approximation. And if we take a look at that, then in the graph here, here's the polynomial approximation written here. So if we notice, we have 2 times x minus 8 to the 0 power, which is just x minus 8 to the 0 power is just 1, right? Anything to the 0 power is 1. So we have 2 plus 1/12 x minus 8 minus 144 or x minus 8 squared over 2 plus 5 over 3,456 x minus 8 cubed over 6, which is 3 factorial. And so there's that cubic approximation. Here's our center 8. And so this looks to be pretty close, closely centered at 8, but the approximation looks to be pretty close all the way back down here to maybe about 1, and maybe all the way up here to like 16 or 17. So we have a pretty close approximation here for quite a bit of this function. Here's a situation where we have a function that is just not even defined at 0. So for this situation, we have to center this somewhere other than 0. So we're going to center this at 1, and we want to find a 4th degree approximation. So this is going to be a Taylor. Again, it's a Taylor because it's if it's centered somewhere other than 0. So we have a center of 1. That's why it falls under the Taylor category. Process doesn't change; it's just a different name. So we have the function, and then we're going to do a 4th degree approximation. So that means we have to find the first 4 derivatives. Okay, so the value of the function is the natural log of x. When we take the derivative of that, we get 1 over x. I'm going to call it x to the minus 1 power, because that's easier for me to take the derivative of. So that's going to be minus x to the minus 2. This is going to be 2x to the minus 3, right? And we bring down the negative 2. Negative 2 times negative 1 is positive 2. And this would be negative 6x to the negative 4. So evaluating these now, we've got to evaluate all of these at the center. So the center is 1. So we need the value of the function at 1. There we go. We need the value of the function at 1, and we need the value of all its derivatives at 1. Matching all of those derivatives is what gives us a good approximation. Okay, so we need the value of all of that information. Then that will give us the numerator of all of the terms in our expression. So the natural log of 1 equals 0. 1 over 1 equals 1. Negative 1 over 1 squared is also 1, as negative 1, excuse me. 2 over 1 cubed, I'm putting this back into its, the denominator is 2. And negative 6 over 1 to the 4th is negative 6. So if we look at these are all the numerators. It's completely wrong. Shit. Yeah. Okay. Those are the numerators of each term. And if you notice also, this also does follow a factorial pattern. This is a 0 factorial. Excuse me, that's not a 0 factorial. This is a 1 factorial. This is a 1 factorial. This is a 2 factorial. This is a 3 factorial. Wow, maybe that's not even should be included. Okay, so starting from here. So writing our 4th degree polynomial approximation then, or P4 of x, writing that polynomial approximation, we have to have it centered, again, we have it centered at 1. So we have our 0th derivative, or in other words, the expression, the value of our function, and then x minus 1 to the 0 power over 0 factorial, so that whole thing is 0. Then we have plus 1 x minus 1. This is where our center comes in to the first power. And then we have minus 1 x minus 1 squared over 2 factorial. And then we have plus 2 x minus 1 cubed being the 3rd derivative over 3 factorial. And then the next one is the next derivative, minus 6 x minus 1 to the 4th power over 4 factorial. So this is our Taylor approximation centered at 1. And yeah, this you can just write as minus 6.